So starting back with number 7, I go to my list of integration techniques and I ask myself, can a constant be pulled out in front? Can I split this up into partial sums, etc.? And I'm not seeing any of these questions that I can answer yes to. But I bet that I could actually make number 7 look like number 6 if I used a technique from algebra called completing the square. So I'm going to write the denominator out off to the side here. X squared plus 8x, and then I'm going to write the 25 plus 25 off to the side. So my middle term is 8x. If I split the coefficient in half, I get 4, and then if I square that, I get 16. So I'm going to add 16 right here to complete the square, but in order to keep my expression balanced, if I add 16, I also have to then subtract 16. So this expression becomes x plus 4 squared, that's the perfect square part, and then 25 plus 16 equals 9. So x plus 4 squared plus 9 is mathematically equivalent to what my original denominator was, x squared plus 8x plus 25. And then I have the advantage of rewriting it and noticing that now it does have two perfect squares, one a constant, one a variable. So my constant is 3, because 3 squared is 9, and my variable is x plus 4, which makes my du a direct exchange to dx. And then I can see that I have, in fact, the form of 1 over a squared plus u squared du. And that turns into giving me an antiderivative of 1 over a, which is 1 over 3 times the inverse tangent of u, which is x plus 4, over a, which is 3, plus c. Okay, so now that we've done number 6 and 7 together, pause your video, give yourself a chance to try number 8 and number 9 by yourself. When you're done working on 8 and 9 by yourself, unpause your video, see if your answer matches mine. Go ahead and pause now. So for number 8, I don't see two perfect squares, one a constant, one a variable. But what I do see is a function inside of a function and a function whose derivative is also present, so I start to think u substitution, where u is my function inside of that square root function, which is x squared minus 2x, and du becomes, with a little factoring, 2 times the quantity of x minus 1 dx. To account for that coefficient of 2 in my exchange, I multiply my integral by 1/2, and then I really just have a power rule, 1/2 times the integral of u to the negative 1/2 du. So I apply power rule and then substitute back in for my expression for u, and I'm left with x squared minus 2x all to the 1/2 power plus c. So for number 9, I do in fact have two perfect squares, one a constant and one a variable. My constant being a equals 1, my variable being u equals e to the x, and that is squared as e to the 2x. So I do in fact have the form of the integral of 1 over a squared plus u squared du, the integral of 1 over the sum of two perfect squares, which will yield an antiderivative with inverse tangent. So following the form precisely, I'm going to have 1 over a, which is 1 over 1, times the arctangent of u, which is e to the x, over a, which is 1, plus c, and just cleaning it up a little bit, I am just left with arctangent of e to the x plus c.